Attention all operators on countdown 1. We're going to start our go-no-go poll for today's flight. Raptor 1.
Go.
Raptor 2.
Go.
Stage 1.
Go.
This Starship is the most powerful rocket ever built. SpaceX has a lot riding on the Starship's success, with the company hoping to go public next month in what is expected to be the biggest initial public offering.
Hold the vehicle.
Do we see anything on the sensors that's a problem?
5, 4, 3, 2, 1.
It's kind of amazing that this window of opportunity is open for life to go beyond Earth. The thing that gets me most fired up is that creating a self-sustaining civilization on Mars would be the greatest adventure ever in human history.
Here is the problem that determines whether humanity ever lives on another world. Visiting a planet is hard. Building the infrastructure to stay there is a category of difficulty most people have not fully reckoned with. Habitats, power systems, water recycling, construction equipment, food, spare parts, all of it has to move beyond Earth repeatedly, at scale, over decades, before a single permanent outpost becomes viable. And right now, no rocket in history was designed to do that. SpaceX is building one. The decision that defines that rocket is its engine, the Raptor. Let's start with what modern rockets actually do well. The fundamental model that has powered spaceflight for 6 decades is launch, deliver payload, discard hardware, repeat. That model works for exploration missions and one-time deliveries to specific destinations. It is entirely adequate for what it was designed to do. The problem is that building permanent infrastructure beyond Earth requires something structurally different. Think about the supply chain that sustained presence on the Moon or Mars demands. Habitats have to get there, along with power systems, surface vehicles, life support equipment, food, water, spare parts, and construction materials. All of it has to move beyond Earth continuously, across years and decades, the same way container ships supply island cities today. Apollo demonstrated that human beings could survive a short visit to another world. Survival for a few days and building the infrastructure for a civilization on another world are problems in entirely different categories. Permanent off-world presence, at its core, is a logistics problem, and you cannot solve a logistics problem with a disposable transportation system. Every mission that discards its hardware starts the cost clock over from zero. SpaceX recognized this and made a fundamentally different design decision. Instead of building rockets optimized for individual missions, it set out to build a transportation system optimized for throughput. The Raptor engine is where that decision became hardware. Most rocket engines flying today use one of 2 combustion cycles, gas generator or staged combustion. Both have powered successful missions for decades, but both leave efficiency on the table by routing some propellant through the turbomachinery and discarding the exhaust rather than feeding it back into the main combustion chamber. The Raptor uses full-flow staged combustion, a design cycle that engineers theorized about for decades and largely avoided building because the manufacturing complexity was considered prohibitive. The Soviet RD-270 came closest to demonstrating it in the 1960s, but never reached flight. The Raptor became the first full-flow staged combustion engine to power a vehicle to orbit on Starship's integrated flight test in April 2023. The practical effect of full-flow staged combustion is that virtually all of the propellant, both methane and liquid oxygen, flows through the system and contributes to thrust rather than being partially exhausted. The result is higher efficiency, more complete combustion, and the ability to operate at dramatically higher chamber pressures than conventional designs can sustain. Raptor 3, the current production version as of early 2026, operates at chamber pressures reaching 350 bar. By comparison, the Merlin engine powering Falcon 9 operates at roughly 97 bar, and the RS-25 engines that powered the Space Shuttle operated at around 207 bar. Raptor 3 delivers 280 metric tons of sea-level thrust, making it the most powerful Methalox engine ever built. By April 2026, SpaceX had produced more than 600 Raptor engines and accumulated more than 40,000 seconds of runtime across all variants. Building a powerful engine is a solved problem in aerospace. Building one capable of surviving repeated operation at those pressures across hundreds of flights with minimal refurbishment is the genuinely new challenge that Raptor addresses. The fuel choice is one of the most consequential decisions in the Raptor's design, and it reaches far beyond the combustion chamber. Most large rockets historically burned kerosene-based propellants. The Saturn V used kerosene, Falcon 9 uses kerosene, and it is dense, energy-rich, and well understood. The downside is that kerosene leaves soot deposits inside engines that require intensive cleaning between flights, limiting reuse cadence. Raptor burns methane, which combusts significantly cleaner, producing far less soot and far less degradation of engine internals between flights. Raptor 3 was engineered to eliminate the external heat shields and fire suppression systems that earlier versions required, internalizing all secondary flow paths and adding regenerative cooling throughout. The result is an engine 36% lighter than Raptor 1, delivering 51% more thrust, with less maintenance required between launches. The methane decision carries a second implication that matters even more to the long-term architecture. The raw ingredients to produce methane exist on Mars. Carbon dioxide from the Martian atmosphere, combined with hydrogen through the Sabatier reaction, produces methane and water. A propellant plant on Mars could produce the fuel needed to refuel starships for the return journey to Earth, meaning missions would draw on local resources rather than carrying all return propellant from home. SpaceX chose methane because the engine performs better on Earth with it, and designed the entire architecture around what that fuel makes possible at Mars. The Raptor sits at the center of a transportation architecture that includes something spaceflight has not previously attempted at operational scale: cryogenic propellant transfer in orbit. Starship missions beyond Earth orbit require more propellant than any single launch can carry alongside its payload. The solution SpaceX is developing involves dedicated tanker variants of Starship that rendezvous with a depot ship in orbit and transfer liquid methane and liquid oxygen before the mission vehicle departs. NASA's Human Landing System contract for Artemis requires SpaceX to demonstrate this capability before the first crewed lunar landing. As of early 2026, SpaceX has conducted initial cryogenic fluid transfer tests, with full on-orbit demonstration flights required before any crewed lunar landing can proceed. The deeper implication is a structural change in how spaceflight works. Missions stop being isolated events constrained by the payload and propellant capacity of a single launch. They become legs in a network where propellant is positioned in orbit and drawn upon by vehicles heading to different destinations on different schedules. Space infrastructure begins with a fuel movement in orbit, and the Raptor's efficiency makes the economics of building and sustaining those depots viable in a way a less capable engine could not. The thrust numbers are impressive. The chamber pressure is unprecedented. The methane chemistry is strategically significant. The core innovation underneath all of it is reusability. The economics of spaceflight change fundamentally when the rocket stops being a single-use item. Every disposable launch is a new manufacturing event, a new engine, new tanks, new avionics, new structure, built and destroyed in roughly 10 minutes of flight. The marginal cost of each mission stays high because the hardware is always replaced. Rapid reuse collapses that cost structure. Raptor was designed from the beginning around high launch cadence and minimal refurbishment between flights. The FAA authorization in April 2025 approved up to 25 Starship launches per year from Boca Chica, a regulatory envelope SpaceX is actively building toward. As of early 2026, all 33 Raptor 3 engines on a Super Heavy booster completed a full-duration static fire test, validating integrated cluster performance at a scale no previous launch vehicle has approached. The cadence SpaceX is targeting makes sustained cargo delivery to the Moon and Mars economically survivable across the decades that permanent outposts require. Colonization is, at its most fundamental level, a supply chain problem, and the Raptor was designed for the scale that problem demands. We should sit with what Mars actually requires, because the Moon already pushes transportation systems to their limits, and Mars is a harder problem in every dimension. The Moon is 3 days away. Mars, at its closest approach, is roughly 7 months away, and that transit window opens only once every 26 months. Rapid abort capability disappears, resupply on short notice becomes impossible, and anything that fails on the surface has to be repaired with whatever was brought along or manufactured locally. That changes the requirements on every system in the transportation stack, and especially on the engine at its center. Landing is its own distinct challenge. Mars has an atmosphere thin enough to generate dangerous heating during entry, while remaining too sparse to slow very large cargo systems efficiently. This is the Mars entry, descent, and landing problem, and it scales harder as payload mass increases. Starship's aerodynamic entry profile was specifically designed to address this by maximizing drag across the vehicle's broad cross-section. Mars only becomes a realistic destination when the transportation becomes repeatable at the scale and cadence that sustained operations demand, and SpaceX is betting the Raptor-powered Starship system is the foundation for making that happen. The Raptor matters in itself as a piece of engineering. Its chamber pressure record, its full-flow staged combustion cycle, its reusability-first design represent genuine technical achievements. The deeper significance is the assumption the engine was built around, that humanity's future in space depends on permanent infrastructure, and that permanent infrastructure requires transportation that is reliable, repeatable, and economically survivable across the timescales needed to build a civilization somewhere new. That assumption changes what you optimize for. It changes how you choose propellants, how you design combustion cycles, and how you think about refurbishment between flights. Every engineering decision in the Raptor traces back to a single commitment. The goal is throughput at scale, sustained across decades. Whether that bet pays off will be answered over the next decade, as Artemis landings begin, as orbital refueling is demonstrated, and as the first Starships prepare for Mars transit windows in the early 2030s. The engineering foundation for what SpaceX is attempting is real, and it is further along than almost anyone predicted 10 years ago. Permanent operations on the Moon, and eventually Mars, depend on one capability above all others: moving people and cargo through space reliably, repeatedly, and at scale. That is the problem the Raptor was built to solve, and the question has moved from whether this engine works to what it makes possible next.